Previously, we've seen something we called trigonometric integrals, which are just integrals that have a whole bunch of trig terms in them. And the basic strategy was that you found some trig identity that allowed you to manipulate a challenging integral into one that was doable with a simple u substitution. Now, in this video, we're going to be talking about trigonometric substitution. There's some integral we don't know how to do, but we introduce trigonometry via a substitution, then we can use all of our different trigonometric identities to transform it into one that we know how to do. So this comes up in a whole bunch of natural contexts, one of which is the problem of finding the area of a circle. This is the circle given by x squared plus y squared equal to 1. It's a circle of radius 1, or more precisely, a quarter of a circle of radius 1. Now, we know what the area of a quarter circle is. We know the area of a circle is pi r squared. If r is 1, then the area of a circle is pi. And if it's a quarter circle, it's just pi divided by 4. And because I've chosen a quarter circle, I can take this equation and I can actually get a function of it. I can solve for y. I can take the positive square root, and I can rewrite this as y equals the square root of 1 minus x squared. Now, we know the area of a circle formula, but where does it come from? How do we derive it? One of the big triumphs of calculus is that we can figure out areas underneath curves. So if I have this curve here, this y equals square root of 1 minus x squared, then I can figure out the area between 0 and 1 of the square root of 1 minus x squared dx, and that better be the answer of pi over 4. So really what I'm trying to do is take this particular integral, and that's something that I'm trying to study. Now, how do I solve it? You might think we could do a u substitution, like, oh, I don't know, it's a square root of blah. So what if we make that inside this 1 minus x squared our u? But then our du is going to pick up an x, and there's no x outside of the square roots, so it just doesn't work out. Well, what else can we do? I'm going to do a different substitution. Just bear with me for a moment of why I'm choosing this. I'm going to choose a substitution x is sine of theta. Notice that this sort of works in the reverse of how we normally do u substitution. Normally we take some complicated, messy function of x and set it to be our new variable. Now we're taking the x itself and setting it to be some function of a new variable. It's sort of backwards for the normal u substitution. But nonetheless, let's take the substitution and let's just see how it goes. If this is our x, then our dx is cos of theta d theta. And if I'm going to transform the integrand, I also have to transform the limits of integration, the 0 and the 1. So if I take the x equal to 0 or the x equal to 1, what theta value do I get out? Now, there's a technicality here. There's a bit of a problem we have to work through because there's an ambiguity here. If you think about what the graph of sine of theta is, it's going to look like this. And if you ask, well, when sine of theta is 0, what theta value is? Well, sine of theta is 0 at theta equal to 0, pi, 2 pi, minus 2 pi, all sorts of places. So there's not just one answer here. Likewise for the value of 1, sine of theta is equal to 1 at pi over 2, but also at minus 3 pi over 2, and many other values. So how do we resolve the ambiguity? I have to choose a region of sine of theta and restrict my domain to just that region that I'm going to talk about. For instance, let me take this region right here that I've highlighted in green between minus pi over 2 and pi over 2. Notice that in this region, the graph of sine theta, it attains all the values between minus and 1, as in this region is big enough. Any possible value that sine theta could ever achieve is achieved by taking a value of theta between minus pi over 2 and pi over 2. But it's also achieved only once, and that's the key idea. In mathematics, we often call this one-to-one, the notion that any value that is attained is only attained exactly once. But the idea is that if I restrict my domain to the green, to this minus pi over 2 up to pi over 2, then I can adjudicate questions like if x equal to 0, what value is sine of theta, and I can adjudicate them uniquely. So in particular, if x is equal to 0, it forces it that theta is equal to 0. That is the only place where sine of theta is equal to 0. And likewise for 1 is going to occur at pi over 2. So now that I've done all this sort of technical stuff, I can plug everything in. I've got my x, I got my dx, and I've got my limits of integration. I plug those in, and what do I get? 0 up to pi over 2, the square root of 1 minus sine squared theta times cosine of theta d theta. Now, what we've done is we've transformed this integral into one with a lot of trigonometric terms in it. And so what am I going to do? I'm going to use the methods of trigonometric integration that we've seen before. One of the things that stands out to me is the 1 minus sine squared. Because I have an identity. I have that Pythagorean identity that sine squared plus cos squared is just 1. And therefore, if I take the 1 minus the sine squared, that's going to get a cos squared inside of the square root. So I get the integral from 0 to pi over 2 of square root of cos squared times another cosine of theta, finally the d theta. Now, you might be tempted, square root of a square, just write cosine there, Trevor. But you have to be careful about the sign. Because when I take the square root of something squared, I lose the plus or the minus. So I have to adjudicate whether it's positive or negative. But thankfully, I have that restriction on my domain. I know I'm talking about thetas between minus pi over 2 and pi over 2. So if I look at what the graph of cosine was, between minus pi over 2 and pi over 2, you see how cosine is all positive in that green selection? So the square root of cos squared, it is just going to be cosine. There is no negative sign that needs to come in. It's just all positive. So I can just replace this and say this is the integral from 0 to pi over 2 of 1 cosine, that's the square root of the cos squared, times another cosine of theta, and then finally multiplied by the d theta. Now it's just a trigonometric integral. We can do the same methods we've done previously. It's an even power, so we'll use that half angle identity. We rewrite that as 1/2 of 1 plus cosine of 2 theta. This is an integral that we're able to do, and so I can go and integrate that. I get theta over 2 minus 1/4 sine of 2 theta. I evaluate between the 0 and the pi over 2, and voila, we get pi over 4, the answer that the area of a circle, that pi r squared, but we were doing a quarter circle, that answer was pi over 4 at the beginning, and indeed we've got pi over 4 now. There actually is a bit of a chart for these kind of things. When we made that choice that x was sine of theta, how did we do that? Well, I just gave it to you in this video. I didn't explain how. In the next video, I'll talk a little bit more how to anticipate it. But if you want, there is this chart here that tells you what substitution to use in what different situations, what the restriction on the domain ought to be, and what trig identity you're going to use. Now, I'm putting this chart up here, but I would actually caution away from using it. I like to think through it, anticipating what trig identity am I going to use? What would be helpful if I have some expression? What should I try to do? Should it be sines, cosines, tangent, or whatever? And I'll talk a little bit more in the next video about how to make those kind of choices, but here is this chart just to get you rolling.